Tonight, we are going to travel to Alpha Centauri, the nearest star system beyond our own sun. And by the end of tonight, you will understand exactly why that journey is terrifying. Not difficult, not ambitious, terrifying. Alpha Centauri sits roughly 25 trillion miles away from the world you are lying in right now, which is a number that sounds large in the way that all astronomical numbers sound large, and which most people quietly file away as impressive without ever really feeling what it means. 25 trillion miles is not the kind of distance that yields to intuition. It does not shrink when you turn it over in your mind. It simply sits there, patient and absolute, and the longer you look at it, the less it resembles anything human beings were built to understand. This video is not just about the physics of that distance, though we will cover the physics in full. It is about the reality of what such a journey would mean for any person who actually attempted it. The biological reality, the psychological reality, the existential reality of leaving everything you have ever known behind at the edge of one solar system and spending a human lifetime, or several, crossing the dark between here and there. The engineering problem is extreme, but the human problem is something else entirely, and that is what we are here to sit with tonight. If you find yourself drawn to questions about where humanity might one day go, and what the cost of going there would actually be, like and subscribe so you can find your way back here. Let's begin. Alpha Centauri is not a single star. And that is the first thing worth understanding, because when most people picture the nearest stellar neighbor, they picture a single point of light hanging in the southern sky. One sun, alone, at a distance. The reality is more layered than that, and in some ways more inviting, though the invitation turns out to be a kind of cruelty the further you examine it. The system is made up of 3 stars. 2 of them, Alpha Centauri A and Alpha Centauri B, orbit each other in a slow gravitational embrace, a binary pair that has been turning around its common center for longer than the Earth has existed. They are, by stellar standards, remarkably similar to our own sun. Alpha Centauri A is slightly larger and brighter. Alpha Centauri B is slightly smaller and cooler. Seen from a distance, they appear as a single bright object. The third brightest star visible in the night sky, outshone only by Sirius and Canopus. But there is a third member of this family, and it is the one that matters most to anyone thinking about where a spacecraft might actually go. Proxima Centauri is its name, and the name is deliberate. Proxima comes from the Latin word for nearest, and it earns that name precisely. It is the closest individual star to our sun by any measurement we have, sitting at a distance of 4.24 light-years from Earth, slightly closer than the binary pair, which lies at 4.37 light-years. Proxima is a small, dim, red dwarf star. Not the kind of object you could see with the naked eye on a clear night, but in 2016, astronomers announced something that changed the way many people thought about this entire region of space. They had found a planet orbiting Proxima Centauri. It was designated Proxima Centauri B, and it is, by the measurements we have, roughly Earth-sized, close enough in mass and orbital distance from its star to sit within what planetary scientists call the habitable zone, the band of distances where liquid water might exist on a surface, where conditions might, under the right circumstances, permit something like life. That discovery is a flicker of something that feels almost like an answer to a question humanity has been asking for as long as it has been looking upward. There might be a world there, a real one that, from the right angle on the right clear night, you could technically point a telescope at and see light from. And this is where the cruelty enters, because the moment you look through that telescope, you're already inhabiting the problem in a way that most people never stop to register. The light reaching your eye left Proxima Centauri 4.24 years ago. You are not seeing the star as it is. You are seeing it as it was, more than 4 years in the past. The light having crossed all of that distance at the fastest speed the universe permits anything to travel. You are looking into a kind of preserved past, a message sent years before it arrived. And the reason for that delay is the same reason the journey there defies everything our instincts tell us about what it means to be far from something. Light travels at 186,000 miles per second. Not per minute, not per hour, per second. In the time it takes a human heart to beat once, light has already crossed from New York to Los Angeles and back again roughly 33 times. If you tried to build intuition from that number, your intuition would fail you, because there is no frame of reference in ordinary human experience that prepares you to feel what that speed actually is. And yet, even at that speed, even moving at 186,000 miles in every single second, crossing the equivalent of the Earth's circumference more than 7 times in the time it takes to blink, light still needs 4.24 years to travel from Proxima Centauri to the ground beneath you. 4.24 years of continuous travel at the fastest speed the laws of physics allow to cover 25 trillion miles of empty, hostile space. 4 years of unbroken motion, without slowing, without pausing, without any object in that void to mark the progress. That is the gap we are talking about. Not the distance between cities, not the distance between continents, not even the distance between planets in this solar system, which already strains the imagination. This is 25 trillion miles measured in units of how long it takes the fastest thing in the universe to cross it. And light can do something no spacecraft we have ever built can do. So if light itself needs 4.24 years to make that crossing, the real question is not whether the distance is large. The real question is how long it would take us. With our actual engines, our actual machines, the fastest thing we have ever managed to launch away from this planet. And that answer is the point where the word close stops being a comfort at all. So the question becomes, how fast have we actually gone? Because when most people imagine the answer, they think of rockets, the Saturn V, the space shuttle, the imagery of fire and thunder, and something rising from the launch pad with enough violence to overcome gravity itself. And those things are genuinely fast in any frame of reference a human being would normally occupy. But the universe does not use the same frame of reference as a human being. And the gap between what impresses us and what is actually required to cross 25 trillion miles is so vast that it does not feel like a gap at all. It feels like a different category of problem entirely. The fastest object humanity has ever built is the Parker Solar Probe, launched in 2018, designed to study the sun by flying closer to it than any spacecraft before it. At its peak velocity, the Parker Solar Probe reaches 430,000 miles per hour. That number, written out, is 430,000 miles in a single hour. To build some intuition for what that means, consider that the distance from New York to Los Angeles is roughly 2,800 miles. At 430,000 miles per hour, the Parker Solar Probe would cover that distance in approximately 6 seconds. Not 6 minutes, not 6 hours. 6 seconds. You could sit down, reach for a glass of water, take one slow sip, and the probe would already be on the other coast. That is the kind of speed that sits completely outside ordinary experience. The kind of speed that has no useful analogy in daily life because nothing in daily life moves anywhere near it. And for a few moments, when you hold that number, 430,000 miles per hour, it feels like maybe the problem is solvable. It feels like we have built something extraordinary enough to be taken seriously by the distances involved. That feeling is worth acknowledging, because the next number is going to remove it entirely. At 430,000 miles per hour, our fastest speed ever achieved, the Parker Solar Probe would need approximately 6,700 years to reach Proxima Centauri. Think about that for a moment. 6,700 years. The entire span of recorded human history. Everything written down, every civilization that has risen and collapsed, every king and empire and language and war and monument since the first human beings began keeping records, all of that fits inside roughly 5,000 years. The journey to our nearest neighboring star system, at the fastest speed we have ever reached, would outlast all of recorded human civilization by more than a third. You could run recorded history from its very beginning all the way to today, and then run it again, and you still would not have given the Parker Solar Probe enough time to complete the trip. That is not a travel time. That is a geological span wearing the clothing of an itinerary. And we have not even left the solar system yet. Sit with that for a moment, because the temptation is to let it slide past as another large number in a script full of large numbers. But 6,700 years is not an abstraction. It means that if the ancient Sumerians had launched the Parker Solar Probe on the day they first pressed symbols into clay tablets, that probe would still be in transit right now, in our present, with centuries remaining before arrival. Every human lifetime that has ever been lived, every generation, every person who was born and grew old and died while the world changed entirely around them, all of that accumulated human time would not be enough. The probe would still be moving through the dark. And this is the fastest we have ever gone. This is the record. This is the achievement that represents the absolute summit of what our species has managed to accelerate away from this planet. It is extraordinary by any human measure, and it is utterly, almost laughably, insufficient for the task under consideration. If anything, the Parker Solar Probe makes the problem clearer by being as impressive as it is. Because if something that reaches 430,000 miles per hour still needs 67 centuries to arrive, then the problem is not an engineering refinement. It is not a matter of building a slightly better engine or finding a more efficient fuel. The problem is structural. The problem is that chemical rockets, regardless of how perfectly they are designed, are operating in a completely different league than the distances involved. Consider the Apollo 10 command module, which in 1969 set a speed record for crewed spacecraft that still stands: 25,000 miles per hour. That speed is genuinely fast. It is fast enough that at launch, the G-forces push the astronauts back into their seats with a physical weight that a person could feel in their chest. And at 25,000 miles per hour, a spacecraft aimed at Proxima Centauri would need more than 100,000 years to complete the journey. 100,000 years ago, anatomically modern humans were still using stone tools and had not yet migrated out of Africa. The Apollo capsule, the crowning achievement of the most expensive and ambitious technological program in the history of our species, would not arrive at our nearest neighboring star until a span of time had passed that predates all of human civilization by a factor of 20. Chemical rockets are not even part of the conversation. So the question that remains, the one the numbers themselves are now demanding, is whether we can build something fundamentally different. Not faster in degree, but faster in kind. Something that operates by a different principle entirely. What would that even require? And is there any reason to believe it could actually be done? So the question becomes, what does fundamentally different actually mean? And does anything in our current understanding of physics or engineering offer a genuine answer? The natural place to look is the propulsion concepts that already exist on paper, or in early development, or in the kind of classified research that occasionally surfaces in academic journals and government archives. There are several of them, and each one, when you examine it carefully, follows the same arc. A theoretical promise that dissolves, slowly but completely, into a concrete impossibility. But before getting to any specific technology, it is worth understanding the underlying trap that catches almost all of them. It is called the rocket equation, and it is one of the more quietly devastating results in all of applied physics. The principle is simple enough to state in a sentence. To accelerate a spacecraft, you need fuel, but fuel has mass, and mass requires more fuel to accelerate, which has mass, which requires more fuel, and so on, indefinitely. The more ambitious the journey, the more fuel you need, and the more fuel you carry, the heavier your vehicle becomes, and the heavier your vehicle becomes, the more fuel you need just to move that fuel. It is a compounding trap with no exit inside its own logic. Engineers sometimes call this the tyranny of the rocket equation, and the word tyranny is not an exaggeration. It is a structural feature of reality that penalizes ambition in direct proportion to how ambitious you are. For interstellar distances, the fuel mass required under chemical or even conventional nuclear propulsion would dwarf the spacecraft itself by factors that become physically absurd before you have even approached a meaningful fraction of light speed. Which brings us to Project Orion. In the 1950s and into the 1960s, a group of serious, credentialed physicists, not science fiction writers, but people who had worked on the Manhattan Project, proposed a spacecraft that would be propelled by detonating nuclear weapons behind it, one after another, in a rapid sequence. The concept was not casual speculation. It was studied rigorously, with real mathematics and real engineering drawings, and the theoretical performance was genuinely compelling. A spacecraft driven by thousands of nuclear pulse detonations could, by the estimates of the people doing the calculations, reach several percent of the speed of light. Several percent of light speed changes the travel time to Proxima Centauri from geological to merely generational, perhaps a century or two, rather than 100,000 years. That is a different order of magnitude entirely, and for a moment in the late 1950s, there were serious people who believed this was the path forward. Then, in 1963, the Partial Test Ban Treaty was signed, prohibiting nuclear detonations in space, in the atmosphere, and underwater, and Project Orion was effectively ended. The political architecture of the Cold War, a treaty designed to reduce the terrifying proliferation of nuclear testing, reached forward and cancelled what might have been the most audacious engineering program in history before it built a single prototype. The idea required the one thing that civilization had just agreed, collectively, to stop doing. And so it stopped. Fusion propulsion presents itself as the cleaner heir to that promise. Hydrogen is the most abundant element in the universe, and fusion, the process that powers the sun, that fuses hydrogen atoms together and releases enormous energy in the process, has been the subject of sustained, serious, well-funded research for more than 70 years. 70 years is a long time. It is longer than the entire history of commercial aviation. It is longer than the entire span of the Cold War. It is longer than the working lifetime of every physicist who has dedicated a career to the problem. And after all of that accumulated effort, after all of those decades of research and refinement and reactor design, humanity has still not achieved net positive energy from a fusion reaction under controlled conditions. Meaning, we have never built a machine that produces more energy from fusion than we put into it. To start the process, we are close. The International Thermonuclear Experimental Reactor, ITER, is being assembled in southern France right now, a collaboration among 35 nations, and the people overseeing it believe it will demonstrate net positive fusion energy in the coming decades. The honest answer is we do not know when or if we will crack fusion on the scale required for propulsion. 70 years of trying has earned us optimism, but not confidence. And even setting aside that uncertainty, a fusion drive powerful enough to push a crewed spacecraft toward Proxima Centauri remains a theoretical sketch, not a design with a construction timeline. Antimatter is where the physics becomes almost philosophically cruel. Einstein's equation, energy equals mass, times the speed of light squared. The one everyone has seen on a poster implies that matter and antimatter, when they meet and annihilate each other, convert their entire combined mass directly into energy. Not a fraction of it, the way a chemical reaction does. Not a portion of it, the way even a nuclear fission reaction does. All of it. The theoretical efficiency of antimatter as a fuel source is essentially perfect, and a kilogram of antimatter annihilating with a kilogram of ordinary matter would release energy equivalent to roughly 43 megatons of TNT, the approximate yield of the Tsar bomber, the largest nuclear weapon ever detonated, the one whose shockwaves circled the Earth 3 times when the Soviet Union tested it in 1961. That is the energy density of the fuel we are discussing. And here is where the physics delivers its verdict with a kind of cold precision. The total quantity of antimatter that humanity has ever produced across every particle accelerator, every laboratory, every experiment ever conducted on the surface of this planet is less than 20 nanograms. 20 nanograms. A nanogram is 1 billionth of a gram. 20 of them would not be visible to the naked eye. If you collected every atom of antimatter ever manufactured in the entire history of human science and used it to power a light bulb, that light bulb would stay lit for a few minutes before going dark. That is the gap between the theoretical promise of antimatter propulsion and its physical reality. We need it by the kilogram, and we have produced it by the nanogram. And those two quantities are separated by a factor of roughly 50 billion. The production problem alone would require infrastructure and energy input that does not currently exist on Earth. And then there is containment. Antimatter cannot touch anything. Any contact with ordinary matter results in immediate annihilation, which means your fuel supply must be suspended in electromagnetic fields with no physical container walls, sustained perfectly for the entire duration of a journey lasting decades. A single failure in containment, not a catastrophic failure, just a small one, a momentary lapse in the field, and your fuel becomes a nuclear-scale explosion, with your spacecraft at its center. You are not carrying propellant. You are carrying a live nuclear weapon that requires perfect maintenance indefinitely to avoid detonating. Each of these technologies arrives with genuine theoretical merit, and each of them breaks on contact with physics, or politics, or the current state of human capability. The pattern is consistent enough that it starts to feel like something more than bad luck. And yet there are other approaches, ones that abandon the idea of brute force entirely, that ask whether elegance and physics working together might accomplish what raw power cannot. The elegant approaches begin with ion drives, and ion drives are real. They are not theoretical. They are not a physicist's whiteboard conjecture. The Dawn spacecraft used them to orbit both Vesta and Ceres, becoming the first probe to orbit two bodies beyond the Moon, and Deep Space One used them successfully in the late 1990s as a deliberate test of the technology's viability. They work by taking a propellant, most commonly xenon gas, and ionizing it, stripping electrons away from the atoms, and then accelerating those ions using electric fields to produce thrust. The exhaust velocity is far higher than chemical rockets, which means more efficient use of fuel, which means the mass problem becomes at least somewhat more manageable. This sounds genuinely like progress, and in the context of our solar system, it is progress, real, useful, tested progress. The thrust generated by an ion drive is roughly equivalent to the force of a single piece of paper resting on the back of your hand. That is not a poetic approximation. That is a fairly literal description of the physical force involved, somewhere in the range of a few hundredths of a Newton, which is the unit we use to measure how hard something pushes. You would not feel it if it pressed against your skin. Applied continuously over months and years in the frictionless vacuum of space, this microscopic push accumulates into meaningful velocity. That is the entire premise. The ion drive is not a sprint. It is a very long, very patient lean in one direction. And over time, that patience translates to speed. Dawn reached velocities that conventional rockets would have made difficult or impossible without enormous amounts of additional fuel. So the question is whether patience, applied at interstellar scales, eventually gets us somewhere. The answer is no, and the reason returns to something we have already encountered. Ion drives require power, substantial, continuous power, to run their ionization and acceleration systems. And in deep space, solar panels become useless almost immediately. The distances involved drain the sun's light to near nothing within the outer solar system. So to run an ion drive at interstellar distances, you need a nuclear reactor on board. A nuclear reactor has mass. That mass has to be accelerated. Accelerating that mass requires more thrust. More thrust requires more power. More power requires a larger reactor. A larger reactor has more mass. The tyranny of the equation does not care whether you have found a clever new propellant or a more efficient exhaust mechanism. It reasserts itself the moment your power source has weight. Ion drives are a genuine advancement for planetary exploration. For interstellar travel, they are insufficient in a way that is not an engineering detail, but a structural problem. So we turn to sails, which carry a beautiful intuition with them. What if the propulsion came from outside the spacecraft entirely? What if instead of burning fuel or ionizing gas, you simply let the light itself push you? This is not science fiction. Icaros, a Japanese spacecraft demonstrated in 2010, deployed a sail in space, and confirmed that solar radiation pressure does, in fact, produce measurable acceleration. The physics is real. Light carries momentum, and when photons strike a reflective surface, they transfer a tiny portion of that momentum to whatever they hit. This has been measured. It works. The force that sunlight exerts on a sail at Earth's distance from the sun is approximately 9 millionths of a Newton per square meter. 9 millionths. To put that in the context of something physical, a square meter of sail at Earth's orbit is being pushed by roughly the weight of a single grain of salt. 1 grain of salt spread across an area the size of a modest kitchen floor. If the sail you're imagining is truly enormous, say a square kilometer, which is already an extraordinary engineering achievement, the total force being exerted on it is still only 9 newtons, roughly equivalent to holding 1.5 kilograms of groceries in your hand, and that force is at Earth's orbit, where the sun is close. As you travel outward toward Alpha Centauri, the sun's light spreads across an ever-widening sphere, and the intensity drops with the square of the distance. By the time you're even a fraction of the way to the nearest star, the sun behind you is no longer providing meaningful push. The sail goes dark. The grocery bag lightens to nothing. Laser sails try to solve this by replacing sunlight with a focused beam, and this is the basic premise of Breakthrough Starshot, which was announced in 2016 with backing from several serious scientific and financial figures. The concept is genuinely different from anything we have attempted before. Rather than accelerating the laser source along with the spacecraft, you leave it behind, you build a massive laser array on or near Earth, point it at a tiny spacecraft, and use the beam's pressure to accelerate that spacecraft to a meaningful fraction of the speed of light. The numbers that Breakthrough Starshot works with are, in their own way, extraordinary. A laser array generating 100 gigawatts. The combined output of roughly 100 large power plants, all focused into a coherent beam aimed at a single object, could theoretically accelerate a spacecraft to 20% of the speed of light. At that velocity, Alpha Centauri is a 20-year journey, not a 6,000-year one. That compression is genuinely significant. The spacecraft being accelerated would weigh approximately 1 gram, the size of a large postage stamp. At that scale, there is essentially no room for the instruments needed to study Proxima Centauri b in any scientific detail, and there is certainly no room for a human being, or a life support system, or anything resembling a return mechanism. The gram-scale probe cannot slow down. There is no braking system because a braking system would have mass. And mass is the enemy. And besides, the laser array you use to accelerate it is 4 light years behind you and cannot reach the destination to slow you down again. This is a flyby mission. The probe passes through the Alpha Centauri system at 1/5 the speed of light and continues into the void beyond. The window for observation and data collection as it passes a planet it cannot orbit is measured in seconds, and the data it collects, assuming the instruments are advanced enough to collect anything meaningful at that scale, must then be transmitted back across 4.24 light years to Earth, where it will arrive years after the flyby, if it arrives at all, given the power limitations of a transmitter that weighs a fraction of a gram. We would be firing a postage stamp into the dark at 20% the speed of light, hoping it catches a glimpse of something interesting as it passes by in a matter of seconds, and then waiting years for the faintest whisper of a signal to tell us what it saw. That is the most realistic near-term proposal humanity has for reaching another star. And we have not even left the solar system yet. Every broken technology, every structural impossibility, every elegant idea that collapses under scrutiny, all of it is still just an attempt at the first step across a distance that has not moved an inch while we have been discussing it. So even the most optimistic proposals for interstellar travel involve serious compromises. But let's imagine we solve all these problems. Let's say we develop a propulsion system that can accelerate a crewed spacecraft to 10% of the speed of light. 10% of the speed of light. That sounds like a solution. It sounds like the moment in the story where the engineering catches up with the ambition, where the numbers finally start working in our favor. And in one narrow sense, they do. 10% of the speed of light is roughly 67 million miles per hour, which is about 40 times faster than the Parker Solar Probe, our current fastest spacecraft. The journey to Alpha Centauri at that velocity takes 42 years. And for a moment, 42 years can sound almost manageable. It sounds like a long expedition, a difficult assignment, the kind of thing that comes with a large paycheck and a hero's welcome on the other side. But 42 years is not a long expedition. 42 years is an entire adult life. Consider what that number actually means in human terms. If you are 30 years old when the ship leaves the solar system, young enough to be physically capable of surviving the journey, old enough to have the experience and judgment such a mission would demand, you are 72 years old when the ship arrives. Every decade of your working life, every year of middle age, every year that your body slowly accumulates the ordinary damage of time, all of it happens inside the same metal walls, under the same artificial light, breathing the same recycled air, surrounded by the same 50 to 100 people, looking out at a void that does not change. You would board that ship as a young adult and step off it, if you step off it at all, as an elderly person who has spent their entire productive life in a corridor they could walk end to end in minutes. The people who send you will almost certainly be dead before you arrive. Your colleagues on Earth, your contemporaries, the researchers who designed the mission alongside you, most of them will be gone, and the ones who remain will be very old. This is the first real lesson of interstellar travel. The problem is not building a faster engine. The problem is that a human life is short, and the universe does not care. And if you wanted to bring enough people to sustain a community across generations, a crew large enough that the mission could survive accidents, illness, and the ordinary attrition of 42 years of living, the numbers climb steeply. 50 to 100 people might maintain a functioning crew for the duration if everything goes reasonably well. But a mission designed to survive every contingency, to sustain itself across more than one human generation, to arrive with enough genetic diversity and social cohesion to do anything meaningful at the destination, that requires several hundred people, possibly approaching 1,000. And every one of those people must be housed, fed, kept healthy, kept sane, kept alive for 4 decades, with no possibility of resupply from Earth, no possibility of rescue if something goes wrong, and no possibility of simply going outside. That last point bears dwelling on. Every spacecraft ever built has been, in some sense, temporary. The astronauts on the International Space Station are 6 hours from home. If something goes wrong, there is a Soyuz capsule attached to the station, and they can be on the ground before the crisis fully develops. Every crewed mission in history has operated within reach of Earth. The Apollo astronauts, at their most distant, were 3 days away. This ship would not have that. It would have nothing like that. Once it passes the outer edge of the solar system and continues into interstellar space, it is utterly alone in a way that no human being has ever been alone. Not in a way that any analogy from ordinary life can adequately capture, because every human analogy for isolation still involves a planet underneath you and an atmosphere around you and the physical possibility of return. So, the ship cannot be a vehicle in any conventional sense. It has to be a world, a self-contained system capable of producing everything its crew needs for 42 years without any input from outside. Food grown internally, air recycled continuously, water recaptured and purified and cycled back through the system indefinitely, medicine manufactured on board, mechanical failures repaired with parts that must be fabricated from whatever the ship carries, because there is no delivery, no technician, no supply chain. The ship is the island. And unlike an island on Earth, there is no ocean to fish, no rain to drink, no soil to grow anything in unless you brought it with you. Now think about what a structure like that actually looks like. A crude interstellar vessel carrying 50 to 100 people for 42 years, with the internal volume to house a functioning biosphere, agricultural capacity, medical facilities, manufacturing capability, and a community of human beings who need space to live without descending into psychological collapse. That is not a spacecraft in the sense of anything we have built. That is a city in a tube, several hundred meters long, carrying everything it will ever need, flying through absolute darkness at 67 million miles per hour. And even that image undersells one specific engineering requirement. Without gravity, the human body begins to destroy itself within months in ways that 42 years would make catastrophic. But that belongs to what comes next. What matters here is the structural consequence. Artificial gravity, generated through rotation, is the only mechanism available to us. And rotation at a tolerable level requires a minimum radius of 100 meters. This is not a preference. Below roughly 100 meters, the Coriolis effect, the sense of deflection that comes from spinning, becomes severe enough that the crew cannot walk normally, cannot pour water without watching it arc sideways, cannot perform basic tasks without continuous neurological disorientation. So the rotating habitat of this ship must be wider than a football field is long, spinning in the void, just to replicate something approaching the ordinary feeling of standing on a floor. That is the minimum. And this minimum structure, carrying its minimum crew, with its minimum supplies and its minimum life support, must function without a single catastrophic failure for 42 consecutive years. Not mostly, not nearly, perfectly. Because in interstellar space, there is no second option. There is no one coming. There is no way home. The engineering must work every day for the entire length of a human lifetime, or the people inside it die in the dark between stars. And the question that immediately follows, the one that the structure of the ship cannot answer, is what 42 years of confinement inside that spinning tube does to the bodies it is trying to protect. So consider what that means. Not as a structural problem, but as a biological one. Because the body that lives inside that spinning habitat is itself a system. And it is a system designed by 4 billion years of evolution to exist in one specific environment, on the surface of a planet with full gravity pulling down on it continuously every second of every day, from the moment it is born until the moment it dies. Remove that gravity, or even approximate it imperfectly, and the body begins to read the absence as a signal. And the signal it sends back is dissolution. Astronauts aboard the International Space Station exercise for roughly 2 hours every day, without exception. Not because it enriches their lives or keeps them mentally sharp, though it may do those things too, but because without that exercise, the body deteriorates at a rate that would be considered a medical emergency on the ground. Bones lose density, muscles waste. The heart, which no longer needs to pump blood upward against gravity, shrinks and weakens. Fluid shifts toward the head, increasing pressure on the optic nerves, distorting the shape of the eyeball itself, degrading vision in ways that do not fully reverse after return to Earth. The immune system, deprived of its normal gravitational context and subjected to the low-level radiation environment of low Earth orbit, begins to behave erratically, mounting weaker responses to pathogens and in some cases misidentifying its own tissue as a threat. And all of this happens in 6 months, on astronauts who are exercising for 2 hours every single day, inside a relatively well-provisioned environment just a few hundred kilometers above the ground. The journey to Proxima Centauri at 10% of the speed of light takes 42 years. That is 84 of those 6-month intervals, stacked end to end, each one compounding the last. Artificial gravity generated through rotation addresses the most immediate cause of this deterioration, and a rotating habitat with a radius of at least 100 meters would restore something close to the sensation of standing on a floor. But even a well-rotating habitat is not the Earth. It is an approximation. The question of whether that approximation is sufficient to prevent skeletal and muscular and cardiovascular decline over 4 decades is one that no human being has ever tested. Because no human being has ever spent 4 decades in space. And the physiological research we have covers at most about a year in continuous microgravity. We are extrapolating from months into decades. And the honest answer is that we do not know what accumulates. And that uncertainty sits inside a larger one, because the body is only one of the systems that must not fail. The International Space Station recycles approximately 93% of the water used on board: urine, condensation, sweat, capturing and purifying it and cycling it back through the crew. 93% sounds impressive. It is impressive. It represents decades of engineering refinement, and it is one of the genuine achievements of long-duration spaceflight. But 93% means that 7% is lost on every cycle. And the ISS can absorb that loss because every few months, a resupply mission arrives with fresh water, among other consumables, launched from the surface of a planet that is never more than a few hundred kilometers below. There is no resupply mission to interstellar space. The ship that leaves for Proxima Centauri carries exactly what it carries, and nothing more arrives. So the recycling rate cannot be 93%. It has to be something approaching total, as close to 100% as engineering can achieve and sustain, maintained without degradation for 42 consecutive years, because every fraction of a percent that is not recovered compounds over decades into a deficit that has no remedy. The water does not come from anywhere. There is no anywhere. There is only the ship and 25 trillion miles of empty, hostile space in every direction. Food introduces the same problem, but without even the partial solution that water recycling offers. Because food cannot be extracted from the crew's own metabolism and returned to the system in any meaningful quantity. It must be grown. The ship must carry functioning agricultural systems, plants, soil or equivalent substrate, lighting, controlled atmosphere, nutrient cycling, and those systems must produce enough calories to sustain 50 to 100 people continuously for the full duration of the journey without a single catastrophic crop failure. A crop failure on Earth is a regional disaster. A crop failure on a ship between stars is a death sentence, not metaphorically but arithmetically. Fewer calories available, distributed across the same number of people, with no possibility of import. The margin is zero. There is no granary to draw on, no neighboring region to trade with, no harvest that can be delayed until next season. Every cycle of growth must succeed, or people begin to die. And when they do not die from hunger, they will eventually face something else: illness, injury, the ordinary and extraordinary medical emergencies that occur in any population of 50 to 100 people across 42 years. On Earth, a serious infection goes to a hospital. A broken bone goes to a trauma center. A sudden cardiac event goes to an emergency room staffed by cardiologists with imaging equipment and surgical capability, and a blood bank, and years of specialized training. The crew of this ship cannot go to any of those places. The crew is the hospital. Whatever medical knowledge exists on board, whatever equipment was packed, whatever surgical skill one or several crew members spent years developing before departure, that is the entirety of available care for 42 years for every condition that arises, for everyone on board. A disease that on Earth would be managed with a specific drug requires that the drug is in the ship's pharmacy, in sufficient quantity, and that it has not degraded in storage. A surgery that on Earth requires 3 specialists and a sterile operating theatre requires, on this ship, whatever the crew can improvise in whatever space they can clear. The ship is not going to a hospital. The ship is the hospital. And what a hospital it is. Sealed, exhausted, several hundred meters long, spinning through the void, carrying everything it will ever have, flying through 25 trillion miles of empty, hostile space, with the nearest help 4.24 light years behind it and growing farther every second. And the threats inside the ship are only half the accounting. Outside the hull, the space the ship is flying through has its own opinion about passengers. Outside the hull, the space the ship is flying through has its own opinion about passengers. And that opinion, it turns out, is not neutral. Most people carry a mental image of interstellar space as emptiness, as the absence of things, as a vast and featureless vacuum that the ship slides through like a needle through water. That image is not wrong exactly, but it is incomplete in a way that becomes catastrophic once you account for the speed the ship is traveling. Because at 10% of the speed of light, the emptiness is not empty enough, not even close. Here is the physics, stated plainly. Kinetic energy does not scale with velocity in a simple, proportional way. It scales with velocity squared. This means that if you double the speed of an object, you do not double its energy on impact, you quadruple it. If you triple the speed, you multiply the energy by 9. At 10% of light speed, a ship is moving at roughly 30 million meters per second, which is a number so far outside ordinary experience that it requires a moment to sit with before its implications become clear. At that speed, the kinetic energy carried by even a microscopic particle becomes something that the word dangerous fails to adequately describe. Consider a single milligram of dust. You cannot see a milligram of dust with the naked eye. If you held a milligram of dust in the palm of your hand, you would not know it was there. It weighs roughly 1,000th of a raindrop. It is, in every ordinary sense, nothing. At 10% of light speed, that invisible fragment of nothing carries the destructive energy of several kilograms of TNT on impact. Not a small explosive, not a firecracker. Several kilograms of high explosive detonating at the point of contact on the ship's hull. The emptiness the ship is flying through is not empty of milligrams of dust. The interstellar medium contains particles, fine, diffuse, but real. And at 30 million meters per second, each one is a small bomb the ship runs into rather than dodges. And we have not even arrived yet. The ship is still in transit, decades from its destination, and already the void is armed. Now scale up slightly. A pebble. Something a child might find on a sidewalk, pick up, and skip across the surface of a pond. A few grams of ordinary rock. At 10% of the speed of light, that pebble carries the energy of a nuclear weapon. This is not a metaphor. This is what the velocity squared relationship means when applied to an object with actual mass. A few grams, moving at 30 million meters per second, releases on impact the equivalent force of a nuclear detonation. The ship does not need to find a dramatic science fiction catastrophe waiting for it in the dark. The ship only needs to encounter a pebble. The obvious response is shielding. Put a thick enough layer of material at the front of the ship and let it absorb the impacts. And shielding does help, up to a point. The Whipple shield concept, which uses spaced layers of material to disperse the debris cloud from a small impact before it reaches the hull, is a genuine engineering solution for particles at much lower velocities. But shielding adds mass. And mass, on this journey, is not an engineering inconvenience. It is the central enemy. More mass requires more thrust to accelerate to 10% of light speed. More thrust requires more fuel. More fuel adds more mass, which requires still more thrust, which requires more fuel, in the recursive spiral that already made the propulsion problem nearly impossible to solve in the first place. The tyranny of the equation does not disappear because you added armor. It returns, wearing the armor's weight, and asks how you intend to pay for it. There is no clean answer. Every kilogram of shielding is a kilogram. The propulsion system must work harder to accelerate. And the harder the propulsion system works, the more the mass budget tightens against every other system on the ship. And even if you solve the shielding problem for physical impacts, there is a second threat that shielding cannot stop. Not fully, not even in principle. Cosmic rays are not particles you can deflect with a thick enough wall. They are high-energy charged particles. Protons, helium nuclei, heavier atomic nuclei, accelerated to extraordinary energies by supernovae and other violent events across the galaxy. And they arrive from every direction continuously. They punch through dense material. They punch through the hull. They punch through the human body. What they leave behind as they pass through biological tissue is ionization, broken molecular bonds, disrupted cellular processes, and most importantly, damaged DNA. A single cosmic ray passing through a cell can break a strand of DNA in a way that the cell's repair mechanisms fail to correct. And the result of that failure, accumulated over enough exposures, is cancer. Over a period of months, the dose is manageable. Over a period of years, the cumulative damage becomes serious. Over 42 years of continuous transit through interstellar space, beyond the protective bubble of the sun's magnetic field that partially shields Earth and even nearby space from the worst of this bombardment, the cumulative DNA damage becomes something that cannot be described as a risk in the ordinary sense. It becomes a statistical certainty. Cancer is not a possibility the crew might face. It is a condition the ship's medical systems must plan to treat repeatedly, in multiple crew members, over multiple decades, with whatever drugs and equipment are on board, and nothing else available. And this is where the communication delay arrives, not as an abstract inconvenience, but as the final seal on the isolation. From the International Space Station, a crew member can call home and hear a voice respond in under a second. The delay is imperceptible. You might forget, listening to the conversation, that the station is orbiting 250 miles above the surface. What once seemed like extreme remoteness, a crew floating in a sealed module circling the Earth, now reveals itself as practically next door. A call home from the ISS takes less time than blinking. On this ship, 1 light year out from Earth, a message sent toward home takes 1 full year to arrive. A response, if one is sent the moment the message lands, takes another full year to return. 2 years for a single exchange. At 2 light years out, 4 years. Halfway to Alpha Centauri, somewhere around 2 light years, and a round-trip message already takes more time than most countries' presidential terms. By the time the ship arrives, a message sent on arrival day will not receive its response for over 4 years. The crew sends words into the dark and waits, not hours, not days, but years for any word to come back. And what comes back is not news. What comes back is already history. Events that happened 4 years before the message was sent. People who may have aged, died, changed entirely in the interval between transmission and response. Real conversation, the kind where 2 people build understanding together in real time, becomes impossible at distances of light years. What replaces it is something more like leaving letters in a bottle and waiting for the tide to eventually, years later, carry something back. The wall between the ship and Earth does not appear all at once. It rises slowly, 1 light year at a time, until the distance is so vast that even the idea of connection begins to feel like a memory of something that no longer quite exists in the form it once had. And that isolation, the kind where years pass between the sending of a word and the receiving of an answer, does something to the mind that the physical threats alone cannot fully accomplish. The body can be shielded, partly. The DNA damage can be monitored, treated, managed within limits, but the mind has its own requirements, and those requirements are not negotiable in the way that engineering problems sometimes are. Researchers who have studied human behavior in extreme confinement, on submarines running silent for months beneath the ocean, on Antarctic stations sealed against polar winter, on the International Space Station, have identified a pattern that appears with enough consistency to be considered a kind of psychological law. It proceeds in 3 phases. The first is what researchers call the honeymoon period. The mission is new, the crew is motivated. The novelty of the environment provides enough stimulation to mask the deeper strangeness of the situation. People are professional, cooperative, energized by the challenge of what they're doing. This phase lasts weeks, sometimes a few months, then it ends. The second phase is conflict. The novelty has worn away. The environment has not changed. The same walls, the same faces, the same recycled air, the same mechanical hum that never stops. But the brain's ability to extract freshness from it has been exhausted. Small irritations that were easy to set aside in the first weeks begin to accumulate. The way someone chews their food, the particular tone of voice someone uses when they are under stress, the unspoken competition over limited resources, limited privacy, limited silence. On Antarctic stations, where crews of 8 to 12 people spend months in darkness and cold that makes going outside genuinely dangerous, researchers have documented depression, interpersonal conflict, cognitive slowing, and what some psychologists describe as an almost physical longing for change. For any change, even a meaningless one, simply because the environment has become so fixed and repetitive that the brain begins to read it as a kind of sensory threat. On submarines, where crews can be submerged for up to 90 days at a stretch, the psychological literature records elevated rates of irritability, sleep disruption, and in longer deployments, a kind of affective flattening where emotional responses narrow and dull. People become versions of themselves that are harder to reach, and this is at 90 days. This is 3 months. The journey to Proxima Centauri takes 42 years. If you tried to construct the arithmetic of it, the multiplication almost refuses to hold. 3 months of documented psychological strain on a submarine. Multiply that interval by roughly 168, and you have 42 years. 168 cycles of 90-day confinement, each one layered onto the previous, none of them offering the release that the end of a submarine deployment provides, which is the surface, the sky, the smell of open air, the return to the world that exists beyond the vessel. For the crew of this ship, there is no surface, there is no sky, there is the hull, and beyond the hull there is vacuum and radiation, and a darkness so complete that even the stars, spectacular as they are, cannot provide the kind of light that a brain calibrated by 4 billion years of Earth evolution is built to receive and interpret as home. Because the sensory loss is not dramatic and sudden. It accumulates the way isolation does, phase by phase, loss by loss. Within the first year, the crew has not felt rain on their skin. Not the abstract idea of rain, the actual physical sensation of cold drops landing on an upturned face, water carrying the smell of soil and ozone and living things up from the ground. That particular combination of pressure and temperature and scent that the human nervous system has recognized as renewal for as long as our species has existed. That is gone. There are no trees. Not the visual representation of a tree on a screen. An actual tree. With texture in the bark and the sound a canopy makes when wind moves through it, each leaf catching air at a slightly different angle, the whole thing alive in a way that a recording cannot capture. There are no birds, not the recorded sound of birds. The actual acoustic presence of a living animal in motion, producing sound as a byproduct of its existence, utterly indifferent to you. Proof that the world continues outside your awareness of it. These are not poetic losses. They are neurological ones. The brain requires input that the ship cannot provide, and the absence of that input is not neutral. The body reads the silence of natural things the way it reads darkness. As information about where it is and where it is increasingly is nowhere that the nervous system recognizes as safe. The third phase, researchers call acceptance. Some people reach it. They find a kind of equilibrium within the confined environment. A recalibration of expectations so thorough that the limits of the ship cease to feel like walls and begin to feel like the ordinary boundaries of the world. Some people never reach it. They remain in the conflict phase, cycling between numbness and friction, managing well enough to function, but never fully settling into the psychological accommodation that acceptance requires. On a mission lasting 42 years, the difference between crew members who reach acceptance and crew members who do not reach it is not a matter of individual resilience that can be screened away. Some portion of a crew of several hundred people will never find that equilibrium, and there is nowhere for them to go. Which brings the question that has been circling this entire account, arriving now not as a challenge, but as a genuine weight. Would you go? Not as a thought experiment where the difficulty is abstract, but as a concrete proposition where the terms are specific. You would leave everyone you know. Not for a year, not for a decade, but permanently. The people you love would age and die while you were in transit, and you would learn of it 4 years after the fact in a message that arrived with a delay so long it had already become history before it reached you. You will never see them again, Not the next morning, not in years, not at all. You would give up the feeling of weather, the experience of seasons, the sound of animals living their lives around you, the smell of a world that is not mechanically maintained. Everything that your nervous system identifies as the texture of being alive on Earth, gone and not temporarily. Gone as a condition of the mission. And some meaningful fraction of the people who said yes to that bargain, who understood the terms, who trained for years and believed themselves prepared, some of them would spend the next 4 decades not at peace with it, but failing, slowly and irreversibly, to be. And that is before you account for what happens when the ship is not just a vessel, but a society. When people form attachments, when relationships become complicated, when the confined world produces not just psychology, but fully human life in every dimension of what that means. And that dimension, fully human life in every dimension of what that means, is worth dwelling on, because it is the part that most accounts of interstellar travel pass over quickly, as if the interpersonal terrain of a closed population can be managed through the right crew selection process and a sufficiently detailed code of conduct. The assumption is that discipline will hold, that the people chosen for the mission, having been screened and trained and psychologically evaluated, will maintain a kind of professional equilibrium across 4 decades, that relationships will remain collegial and stable, that the social architecture of the ship will persist in roughly the form it was designed. This is not how human beings work. This is not how human beings have ever worked, in any environment, under any conditions, regardless of how carefully the participants were selected. Romantic attachments form in closed environments. They form faster and more intensely than they form in open ones, because the pool of available people is fixed, because proximity is constant, and because the emotional weight of shared isolation creates bonds that would take years to develop in ordinary life. This is documented in Antarctic stations, in submarines, in long-duration spaceflight research. The same environment that produces conflict and cognitive stress also produces deep attachment. Sometimes between people who had not anticipated it, sometimes between people whose pairing creates friction with the rest of the crew. A relationship that ends badly in a city is something you walk away from. You go to a different neighborhood, you find a different social circle, you give yourself distance and time. On a ship traveling between stars, the person you ended badly with is at the same table at every meal for the next 3 decades. And the person they became close to after you is 3 berths down the corridor. There is no leaving. There is no neighborhood that does not contain both of them. The emotional geometry of a few hundred people in a sealed environment, accumulated over 42 years, does not resolve into tidiness. It compounds. And then there is the question that the mission planners would prefer to treat as an engineering problem solvable by policy, which is what happens over 42 years when birth control fails. Not whether it fails, it will. Over 4 decades, across a crew of several hundred people, the statistical likelihood of at least one unintended pregnancy is not a remote edge case to be designed around. It is a near certainty to be planned for. What that means in practice is that children will be born on this ship. Children who had no voice in the decision to leave Earth. Children who will grow up in a vessel traveling at a significant fraction of the speed of light between 2 star systems, for whom the concept of a natural horizon is not a memory but an abstraction, something they have read about, something other people describe, a thing that exists somewhere beyond the whole, but that they have never encountered and will not encounter until the ship arrives, if it arrives, and if they survive to see it. A child whose entire world is a hallway, who has never felt wind against their face because there is no weather inside a spacecraft, who has never seen an animal moving freely through a landscape it chose, who has never looked up at an open sky. Sit with that for a moment. A person who never chose this, who has never seen a horizon, never felt wind, and whose entire world is a hallway. And beyond the psychological reality of that childhood, there is a biological question that remains genuinely unanswered, because we have never studied it. The effects of microgravity or even carefully managed artificial gravity on fetal development. on the formation of bones and muscles and organs in an environment that is not the one those systems evolved to inhabit, are not understood. The human body spent 4 billion years developing inside the gravitational field of Earth. Everything about the way a fetus grows, the way bones calcify, the way the cardiovascular system learns to pump against resistance, was shaped by that field. What happens to that process in an environment that approximates Earth's gravity through rotation, but does so imperfectly? And that surrounds the developing organism with radiation levels no hospital would consider acceptable. The honest answer is that we do not know. The research has not been done because the situation has never existed. A child born on that ship would be, among everything else, a participant in an experiment that no ethics committee would ever approve. And across the decades that all of this is accumulating, the attachments and their complications, the children and their questions, the grief and the adaptation, the ship is also doing something quieter. Something that would be nearly invisible from the inside, but unmistakable from the outside, which is that the people on it are drifting. Language drifts in closed populations. Even on Earth, where communities share a planet and a broader culture, dialects evolve measurably within a single generation. New words form, old pronunciations shift, grammar bends in directions that reflect the specific pressures and experiences of the group. In a population of 50 to 100 people, sealed from any external linguistic influence for 42 years, that drift would be faster and more total than anything you would observe in a city or a country. The crew that depart speaking the languages of Earth would, by arrival, be speaking versions of those languages that the people they left behind might struggle to follow. New rituals would emerge from the specific texture of life on the ship, ways of marking time, of acknowledging grief, of celebrating the small thresholds that take on meaning when larger ones are unavailable. A new culture, assembled from the wreckage of the original one and shaped entirely by the constraints of the environment that produced it. The crew would stop being the people who left. They would stop being, in any meaningful sense, Earthlings. The journey does not transport people. It replaces them, slowly, incrementally, through the accumulated pressure of years, so that what arrives at Alpha Centauri is not the crew that departed Earth, but the thing that crew became on the way there. And then there is the question of what happens when you arrive. This is the assumption that has been carrying the listener, carrying perhaps even the crew, through every layer of what has been described. The psychological erosion, the radiation, the grief, the children who never chose any of it, the culture that quietly replaced itself over 4 decades. All of it endurable, theoretically, because at the end, there is a destination. There is a world. There is the thing you went for. Except that assumption rests on a condition that has been almost entirely absent from the conversation. And that condition is this: you have to actually stop. Acceleration and deceleration are not different problems. They are the same problem, stated twice. Every joule of energy required to push a ship from rest to 10% of the speed of light must be matched by an equal effort to bring that ship back to rest at the other end. The physics does not allow a discount. You cannot spend all your fuel getting there and expect the destination to catch you gently. One proposed solution for slowing a craft against a star's solar wind: a magnetic sail. Using the pressure of charged particles streaming outward to act as a brake works reasonably well in theory near a star like our Sun, which produces a robust, consistent outflow of plasma. Proxima Centauri does not do that. It is a red dwarf, a star of 12% the mass of our Sun, producing less than 1% of the Sun's luminosity, and the wind it breathes into surrounding space is too thin, too sparse to provide the braking force a magnetic sail would require. The mechanism that might slow you down near a Sun-like star fails precisely at the star you're trying to reach. So consider what that means in practice. 42 years of travel. 42 years of the journey described above. The bone loss, the isolation, the grief, the children born into hallways, the language drifting, the culture assembling itself from whatever the original mission left behind. And if no adequate deceleration system exists, the ship does not stop. It passes through the Alpha Centauri system at 10% of the speed of light, which is roughly 67 million miles per hour. And the window of close observation, the only payoff for everything that was given, is measured in hours. A few hours of sensors and cameras pointed at something you spent 42 years approaching before the ship carries you out the other side and into the void beyond, with no way back and no way to stop. The cost of the journey was a lifetime. The return on that cost was an afternoon. Sit with the proportion of that. But suppose the problem is solved. Suppose the deceleration question has an answer. Through some technology not yet built, perhaps a laser array at the destination end, perhaps something unimagined, and the ship slows and enters orbit around Proxima Centauri b. This is the moment the entire mission was designed to reach. This is the world. Proxima Centauri b orbits its star every 11.2 days. That is not 11.2 years. That is 11.2 days, because the planet sits roughly 4.6 million miles from Proxima Centauri. To understand what that distance means, consider that Earth orbits our Sun at approximately 93 million miles. Proxima b sits at roughly 5% of that distance, not a slightly tighter orbit, but pressed so close to its star that a year there lasts less than 2 of our weeks. If Earth occupied that same position relative to our Sun, the sky above you would be filled with a star so enormous and so close that the heat alone would have rendered the planet uninhabitable before life had any chance to begin. At that proximity, and around a star of that mass, the gravitational forces involved are not gentle. They are tidal, the same physics that keeps one face of our moon always pointed toward Earth. And they lock the planet into a permanent orientation. One side of Proxima b faces its star forever. The other side faces the darkness forever. The day side, bathed in continuous stellar radiation at close range, reaches temperatures of around 300 degrees Celsius. The night side, receiving no light at all across its entire surface, drops to extremes of cold that the atmosphere can barely mediate. Between these two regions, at the boundary where permanent day meets permanent night, a line called the Terminator, there exists, in theory, a narrow strip of the planet's surface where temperatures might fall within a range that liquid water could survive. A thin ring of permanent twilight, wrapped around a world that is otherwise split between a furnace and a void of cold, with the pressure differential between those two extremes driving winds of hurricane force across the only strip of ground that might, under the most careful interpretation of the word, be called livable. And none of that accounts for the star itself. Proxima Centauri is not a calm star. Red dwarfs, despite their small size and low luminosity, are energetically violent in ways that have nothing to do with their light output. They produce flares, sudden eruptions of radiation and charged particles, that are hundreds of times more intense than the most powerful flares our Sun generates. The surface of Proxima b, sitting at 4.6 million miles from a star that regularly bathes it in radiation events of that magnitude, with little certainty about whether the planet retains enough atmosphere to provide meaningful shielding, receives something more like periodic bombardment than steady starlight. The habitability question is not whether the Terminator ring is the right temperature. The question is whether anything survives the flares long enough for temperature to matter at all. This is the planet that was introduced early in the conversation as a reason for hope. Earth-sized, in the habitable zone, the closest possibly hospitable world to our own. That description is technically accurate in the way that a desert is technically an open space. The classification was offered as an invitation, and what has been waiting behind it all along is something far less welcoming. The crew gave everything for this. They gave rain and open sky and the sound of birds and the smell of the air after a storm. They gave relationships and the ability to walk away when a relationship went wrong, and the freedom to be alone in a crowd, and the experience of seasons, and the feeling of wind. They gave 42 years of one another, sealed inside a moving hull, watching their bodies change and their culture drift, and their children grow up without horizons. All of this surrendered in the direction of a world that may be a sterilized rock. tidally locked, flare-scorched, with a habitable strip so narrow and so wind-torn that calling it a home requires a willingness to abandon almost everything the word has ever meant. That is what arrival looks like. And the journey there has already asked for everything it could take. And yet, sitting with all of that, the tidally locked world, the flare-scorched surface, the hurricane winds tearing across the only strip of ground that might not immediately kill you, there is still one more reckoning that the conversation has not yet arrived at. It is quieter than the radiation and slower than the deceleration problem. And for that reason, it may be the most devastating of all. Consider the timeline of the mission itself. You launch in whatever year the technology and the will and the funding finally converge, and you begin the 42-year crossing. 42 years. And while you travel, Earth does not stop. The laboratories keep running. The engineers keep working. The physicists who were graduate students when your ship cleared the solar system have now had entire careers, and those careers have produced things. Some of them have produced propulsion research, and sometime in the middle of your crossing, perhaps 20 years in, perhaps 30, a new mission launches. A faster one, built on technology that simply did not exist when you left. Technology that your departure may have helped motivate. Because you went first and your going proved it was possible, and the people watching you leave spent the next 2 decades figuring out how to do it better. And this new mission, with its superior drives and its lighter craft, and its decades of accumulated refinement, travels at a meaningfully higher fraction of the speed of light than you do. Not dramatically faster, perhaps, but fast enough. Fast enough that you receive a message one day, deep in the crossing, years from home and years from arrival, and the message informs you that a second ship has launched. And based on current projections, it will arrive at Proxima Centauri before you do. Sit with that for a moment. You left everything. You gave 42 years of your life in a sealed environment, watching the people you loved age alongside you, watching your body change in ways you could not fully reverse, crossing 4.25 light years through silence and radiation, and the accumulated psychological weight of confinement measured in decades. You gave all of that. And the message in your inbox tells you that someone is going to beat you there, and that someone did not have to give what you gave, because you gave it first, and your giving created the conditions for a better attempt. How would you feel? Angry, perhaps, though the anger would have nowhere rational to land. Betrayed, perhaps, though no one betrayed you. The universe simply kept moving forward while you did too, at different speeds. Devastated, in the specific way that devastation feels when the sacrifice was real and complete, and the reward was not withheld so much as quietly transferred elsewhere. Or perhaps, after a long enough silence, something stranger. Relief. Relief that at least someone will get there. That the destination will not wait forever unvisited. That the species which sent you first did not abandon the project just because you were already in transit. There is something in that framing that might be called noble. There is also something in it that might be called cold comfort, which is not the same thing as warmth. This is the weight paradox, and it does not have a clean resolution. If every generation of mission planners decides to hold off, to wait for better drives, better shielding, better life support, better propulsion, then no mission ever launches, because there will always be a reason to believe that something better is coming. The technology curve does not flatten on command, and the argument for waiting is never weaker than the day you make it. It only grows stronger as the years accumulate. If you always wait for the next breakthrough, you wait forever. But if you go too early, you commit an enormous expenditure of lives and resources and political will to a mission that a faster ship, launched 30 years later, will simply overpass. The trap closes from both directions. Wait, and you never go. Go too soon, and your going is wasted. There is no clean answer sitting between those two exits. Whether the willingness to go anyway, knowing you might be overtaken, knowing the mission that costs you everything might be remembered as a footnote to a better attempt, represents the purest form of sacrifice or the purest form of foolishness is a question the narrator will leave where it belongs, which is open. But people would still go. And the question of why anyone with full knowledge of the journey, the destination, the radiation, the confinement, the deceleration problem, the flares, the weight paradox, why any human being would raise their hand and say yes, that is the life I choose. That question deserves a serious answer. The first answer is survival, and it is the longest in its timescale. Our sun is stable now, but it will not always be. In roughly 1 billion years, its output will have increased enough that Earth's oceans begin to boil. Not metaphorically, not gradually in ways that life could easily adapt to, but in the final, civilization-ending sense of the word. In roughly 5 billion years, the sun exhausts its hydrogen fuel, expands into a red giant, and the inner solar system, the region where Earth currently orbits, becomes the interior of a star. The timeline is vast enough that it barely registers as urgency against a human lifespan, or against recorded history, or against anything we typically call the future. But the timeline is real. The clock is running. And if the species intends to survive beyond its home star's lifespan, it has no option except to leave, eventually, for somewhere else. Alpha Centauri is the closest candidate. The argument for going is, in that framing, simply the argument for the species continuing to exist in the very long run. The second answer is curiosity, which is less grand but more immediate and possibly more honest. The third is legacy. The need to have done something that will still matter after you're personally gone, which the crossing would accomplish in a way that almost nothing else in a human life can match. And the fourth is the drive to explore, which is older than agriculture and harder to argue away than any of the rational objections. Because it does not operate on rational logic, it operates on something prior to logic, something that has been present in the species since before it had the language to name it. None of these answers fully dissolve what the journey demands. They coexist with the dread, not replace it. The 42 years are still 42 years. The radiation is still there. The destination is still a possibly sterilized rock on the wrong side of a flaring star. The motives are real, and they are insufficient, and people would go anyway. And the question of what catastrophes might find them in the crossing, catastrophes beyond the ones already mapped, is a question the journey itself would answer, 1 decade at a time, with no ability to turn around. What that journey would answer, though, is not purely philosophical. Some of the answers would arrive without warning, in the form of events that no amount of planning fully prevents, and that training can rehearse but never truly prepare a person for, because the training happens on Earth, with an exit door, and the event itself does not. Consider what happens when a micrometeorite, not a boulder, not an asteroid, but a fragment of rock the size of a grain of rice, strikes the hull of a ship, traveling at 10 to 20% of the speed of light. The ship is moving at roughly 30 to 60 million meters per second, relative to the debris field it passes through. At those velocities, the relative speed between the ship and even the smallest object is not a collision. It is an explosion. The grain of rice-sized fragment carries the kinetic energy of a small explosive device, and the whole, however reinforced, was designed to absorb a great deal, but not at those speeds. And if the hull is breached in a pressurized crew compartment, the cabin begins to decompress immediately. Without a pressure suit, the human brain has approximately 15 seconds of useful consciousness before it loses function. Not 15 minutes. Not 15 seconds to think clearly, and then a gradual fade. 15 seconds of functional awareness. Enough to understand what has happened. Enough to look at the breach. Enough to look at the people around you. And then nothing that could be called useful thought remains. The gap between hull intact and everyone in that section dies is measured in a breath. That is the margin. That is the window the crew would have to work inside. Now, if the breach is contained, if the compartment is sealed fast enough, if enough of the crew survives in other sections, someone has to go outside and repair it. Someone has to suit up, exit the ship, and work on the exterior of a vessel moving through interstellar space at a fraction of the speed of light, surrounded by a cosmic radiation environment that, over the course of a full transit, already represents a statistical certainty of serious long-term damage. An EVA in that environment, extended and unshielded in the way an exterior repair would require, does not represent an elevated risk. It represents a guaranteed outcome. The person who goes outside is accepting a slow, painful physiological decline as a condition of going. They are not gambling. They are trading their future health, and likely their future years, for the continued survival of the crew. We have a word for that kind of exchange, and it is not a technical term. It is a moral one. We do not know what a human being would actually do in that moment. We have simulations and analogies, but no one has ever faced a choice like that. No one. There are Earth-based isolation studies, Antarctic winter over programs, years-long confinement experiments designed to model what deep space crews might experience, and those studies produce valuable data about psychology and group dynamics and stress responses. But they stop at the door. The researchers can observe the volunteers. The volunteers know the researchers are watching. The ship has no researchers. The ship has only the crew, the breach, and the 15-second clock. The second scenario does not arrive with a bang. It arrives quietly, possibly undetected for days in the form of a fever, or a rash, or a symptom that one crew member attributes to fatigue, and does not mention until it becomes impossible to ignore. Pathogens that human bodies carry in dormant or suppressed states, viruses and bacteria that the immune system keeps quiet under normal conditions, can reactivate under prolonged stress, under radiation exposure, and under the kind of immune dysregulation that 42 years in space would almost certainly produce. Beyond reactivation, radiation mutates biological material. A pathogen that entered the ship harmless or manageable might not remain either. The closed environment of an interstellar vessel, in which every breath is recycled and every surface is shared, and every person is within a few hundred meters of every other person at all times, is not a place where an outbreak can be isolated by asking someone to stay home from work. Quarantine on this ship means sealing off a section. It means cutting that section off from the shared life support loop, rationing its air, managing its waste, and communicating with its occupants through whatever interface survives the isolation. And if the pathogen spreads faster than the quarantine contains it, or if the affected crew members deteriorate beyond the ship's medical capacity to manage, the mission planning documents that preceded the launch, the ones written on Earth by committees in rooms with windows, may have included a variable that no press release ever named directly. Euthanasia may have been on the table, not as a failure mode, but as a contingency, as a line item in the calculus of keeping the ship's remaining population alive long enough to reach the destination. These are not science fiction scenarios constructed to make the journey sound dramatic. Over a crossing of 42 years, a closed system carrying several hundred human bodies through one of the most hostile radiation environments in the solar neighborhood, these are statistical realities. The question is not whether something like this happens. The question is which form it takes, and in which decade, and whether the people who remain have what they need to survive it and keep going. There is a version of this story that ends before the destination. A version in which a vessel launched from Earth, carrying people who trained for years in isolation simulations, who gave up their families and their futures and their children and their sky, arrives at Alpha Centauri decades after departure, and does not answer a hail. And decades after that, a second mission, traveling faster because the technology caught up, finds it. Not broadcasting, not drifting with survivors in cold sleep. Just there, in the dark, at the edge of the target system, with its hull intact or not, with its record still running or not, with its cargo of frozen bodies and preserved logs, and the quiet evidence of everything that went wrong in the years when no one on Earth could hear them. Not a failure in the way that word is usually used. Something more than that. A monument to the distance between intention and arrival, between the courage it takes to leave and the luck it takes to get there. That image, a ship found, a crew lost, a message from a crossing that no one survived, is not a thought experiment to be moved past quickly. That is the shape that maximum sacrifice takes in this context. That is what it means to have gone anyway, and to have been answered by the crossing itself, and to have no one left to receive the answer. And the fact that we would, in all probability, keep sending ships after finding it, that says something about the species that is worth sitting with for a moment before the argument moves any further forward. And yet, the ship found drifting, the crew lost, the logs still running. That image does not exhaust the weight of what a mission like this actually means. Because the people aboard that vessel were not the only ones whose lives were permanently altered the moment the launch window opened. The moment a crewed ship departs for Alpha Centauri, something changes for everyone who remains behind as well. Something changes for the species in ways that have no precedent in any prior act of exploration. Consider the problem of communication first, because it is deceptively simple on its surface, and genuinely monstrous once you sit with it. The ship travels for 42 years. Along the way, it sends transmissions home at the speed of light. Earth replies, but Proxima Centauri is 4.24 light-years away, which means that any signal sent from Earth takes 4.24 years to arrive, and any reply from the ship takes 4.24 years to come back. The minimum round-trip time for a single exchange is just over 8 years. Not 8 days, not 8 months, 8 years. If something goes wrong aboard the ship, and a message is sent home asking for guidance, the earliest possible response arrives 8 years later. The people who sent the question may no longer be alive to read the answer. The people who wrote the answer may no longer be in the roles they held when they wrote it. Imagine sending a letter to someone you love, knowing with absolute certainty that the earliest possible reply will arrive on the day your child turns 8 years older than they are right now. That is not a communication delay in the ordinary sense. That is the effective death of real-time governance. Any authority Earth believes it holds over that ship is, in practical terms, an illusion. The crew does not have a chain of command that functions. They have a record of what Earth once said, and whatever decisions they face in the decades between transmissions, they face alone. This means that the moment the ship clears the solar system, humanity becomes a 2-star species. And a 2-star species that cannot, in any meaningful sense, govern itself as one. There is currently no legal framework for this situation. Planetary protection protocols exist for the solar system. The meticulous sterilization procedures before a spacecraft touches Martian soil. The clean rooms, the surface contamination thresholds measured in parts per billion. These exist because the scientific and political communities agreed that they should. They were negotiated over years, enforced imperfectly, updated as missions changed. But those protocols stop at the boundary of what we can reach and monitor and respond to within a reasonable time frame. For a vessel 4 light-years away, doing something irreversible to a planet orbiting another star, no such framework exists. None has been written. None could be enforced if written. The ship's crew acts, and Earth finds out years later. And the divergence does not stop at governance. Over generations, it reaches into biology itself. Isolated populations change. That is not a theory. It is the mechanism that produced every human variation you can observe across Earth's continents today. Small groups, separated by ocean or desert or mountain range, with no gene flow between them, diverge slowly but inevitably over thousands of years. The same force that operated across human history would operate across star systems. Except now, the barrier is not an ocean. It is 4.25 light-years of absolute void, with no crossings possible, no travelers bringing genes from one community to the other, no mixing. A colony at Alpha Centauri, if it survived for several thousand years, would not be a distant branch of humanity in the poetic sense. It would be a diverging lineage in the biological sense. Given enough millennia, what began as a crew of several hundred humans would become something measurably distinct from the species that sent them. That is not alarming in the way that requires alarm. It is simply what biology does when you remove all connection between populations across sufficient time. The same force, now operating at interstellar scale with no return. Then there is the question of how you find them in the first place. Because navigation across light years is not the same problem as navigation across an ocean, or across the solar system, or even across the distance between Earth and Mars. The Sun itself is moving through the galaxy at roughly 500,000 miles per hour. That is not the Earth orbiting the Sun, that is the entire solar system hurtling through the Milky Way on its own arc, carrying every planet and every satellite and every spacecraft we have ever launched along with it. Alpha Centauri is also moving on its own trajectory, at its own velocity, in its own direction. By the time a ship launched today arrives in that system 4 decades from now, neither the point of departure nor the destination will be where they appear to be at the moment of launch. The navigator is not aiming at a star. The navigator is calculating where that star will be in 4 decades, accounting for both systems' motion through the galaxy, and then aiming at a point in space that does not yet exist and cannot be confirmed until the ship is already committed to it. Any error in that calculation, any small drift in the initial trajectory that compounds over 42 years of travel, does not mean arriving slightly off course. It means missing the target system entirely, crossing through empty space where the star was supposed to be, and having no mechanism for course correction once the error becomes apparent. And this is before accounting for the relativistic Doppler shift that affects how signals and measurements behave at 10% of the speed of light. The mathematics is not impossible, but it allows very little room for the kind of accumulated small errors that characterize every long-distance system humanity has ever operated. And someone has to pay for all of this. The International Space Station cost roughly $150 billion to build and operate, spread across the United States and Russia and the nations of Europe and Japan and Canada, negotiated over decades, justified at every budget cycle by its proximity and its ongoing scientific return. Whatever an interstellar mission costs, and the honest estimates run from hundreds of billions to figures that approach the total annual economic output of medium-sized nations, it would require a commitment of resources and political will that no single nation could sustain alone, and that no international coalition has ever maintained across the timescale required. Barnard's star is 6 light-years away. Wolf 359 is 7.9. Lalande 21,185 is 8.3. Even the nearest cluster of potentially reachable destinations represents a commitment measured in generations and in budgets that would dwarf anything humanity has collectively organized in its roughly 5,000 years of recorded civilization. But the most irreversible expansion of stakes, the one that makes everything else feel manageable by comparison, is the possibility that the crew arrives and finds something. Not a dead planet. Not a frozen wasteland. Something. Life, or evidence of life, or the faint signal of a structure that did not form by any natural process the crew can identify. In that moment, a crew of several dozen human beings, more than 4 light-years from Earth, with a minimum 8-year wait before any reply can arrive, would be the entirety of humanity's presence at the first encounter our species has ever had with something outside itself. They could not ask permission. They could not convene a panel. They could not wait for consensus from the 8 billion people they left behind. Whatever they chose to do, approach or hold back, transmit or stay silent, make contact or observe, they would be making that choice for all of humanity with no backup, no guidance, and no possibility of reversing whatever they set in motion before Earth even knew it had begun. That is not a mission. That is a civilizational fork, held in the hands of a few dozen exhausted travelers who have been awake for decades inside a metal corridor and who have not seen rain in longer than some of their children have been alive. And so let's return to the human experience one more time. Imagine you are part of the crew, 10 years into the journey. You have been awake for 10 years inside a metal corridor, and Earth is behind you, somewhere in the field of stars that fills the small observation window you return to, again and again, because it is the only place on the ship that feels like looking at something real. You know, intellectually, which direction Earth is. You have been told the coordinates, but when you press your face close to the glass and look into that specific region of sky, you cannot pick it out. Earth is a point of light, indistinguishable from any other star, lost in a field of 10,000 identical points, anonymous among everything else the universe has placed there. The sun itself, the star your species evolved beneath, the one that warmed every ocean and every continent, the one that your body still expects to rise each morning, is simply another small light in a field of small lights. You cannot tell it apart from the stars of other systems. You cannot find home by looking. And that fact, quiet and clinical as it sounds, is one of the loneliest things a human being has ever had to absorb. That is where the terror lives. Not in the engineering problems, not in the radiation tables, not even in the collision odds that you have already read too carefully. It lives in that window, in the moment your eyes sweep across the starfield and find nothing that answers back. But sit with that image for a moment longer, because there is something else in it. Something that takes longer to see. The crew member at the window is grieving. That is the only honest word for it. Grieving a planet that still exists, that still has its oceans and its weather and its particular quality of afternoon light. Grieving something that was not taken from her, but that she chose to leave behind, fully knowing what the leaving would cost. And the grief is real, and it should be honored. And it is also, when you pull back far enough, the most human thing she could possibly be doing. Because this is what our species does. This is what our species has always done. We have been human beings, in the anatomical sense, for roughly 300,000 years. 300,000 years of our particular bodies walking the surface of one small planet, thinking our particular thoughts, burying our dead and marking our time. And for most of that span, the vast, dark, unrecorded majority of it, we lived in Africa, in the landscape where we first became recognizably ourselves. And then, somewhere between 60 and 100,000 years ago, small groups of us began to walk out. Not because they knew what was beyond the horizon, because the horizon was there, and something in us would not leave it alone. They crossed into terrain no human had ever seen, in bodies that were not built for cold, with tools made of stone and wood and bone, following the edge of their knowledge until the knowledge ran out and they kept going anyway. They crossed deserts. They crossed mountain ranges. They crossed bodies of water in vessels that had never been tested in open ocean. They reached the Americas and Australia and the islands of the Pacific, navigating by stars in skies that no human eye had ever learned to read. And they did all of this without a destination, without a map, without certainty that anything survivable lay on the other side. That pattern, several 100,000 years of restless, costly, grief-laden outward movement, is not an accident of history. It is the signature of what we are. Consider how young we actually are as a civilization, and the stacked timescales become almost dizzying to hold at once. We have had written language for roughly 5,000 years. The Sumerians pressing their first marks into clay, the slow accumulation of recorded thought and organized society. 5,000 years is a long time in human terms. It is barely a breath in the 300,000 years our species has spent on this planet. Then, consider that the industrial age, the period in which we began converting stored energy into mechanical power and transforming the physical surface of the Earth, is only about 250 years old. And then consider this. We have been a spacefaring species for fewer than 70 years. Fewer than 70 years since the first human being left the atmosphere. Fewer than 70 years since we first looked back at Earth from outside it. 300,000 years of existence, 5,000 years of civilization, 250 years of industry, 70 years of spaceflight. We are not a mature species reaching the edge of its capabilities. We are infants who have only just looked up and noticed that there are other rooms. And yet, in those 70 years, we went from a small metal ball beeping in orbit to walking on the moon. We sent probes past the edge of the solar system. We built a telescope that photographs light from the first billion years of the universe. We have already identified a world orbiting Proxima Centauri, 4.24 light-years away, inside the zone where liquid water might exist on its surface. 25 trillion miles of empty, hostile space, and we have already named the destination. We are not wondering whether a target exists. We are arguing about how to reach it. The explorers who walked out of Africa did not know they were founding the human presence on every other continent. They were just walking toward the next ridge. The sailors who crossed the Pacific in outrigger canoes, navigating by wave patterns and star risings, did not understand that they were completing the settlement of an entire ocean basin. They were following something they could not have named precisely. Some orientation toward the unknown that their bodies and their culture had built into them over countless generations. The mountaineers who reached the poles and the summits knew exactly how likely they were to die and went anyway, not because death didn't frighten them, because the other side of their fear was something they could not turn away from. Most likely, when a ship finally crosses that 25 trillion miles and arrives at Alpha Centauri, it will find empty worlds. Airless rock and frozen plains, and the red glare of a dim star illuminating surfaces where nothing has ever moved under its own power. That is the most statistically probable outcome, given what we know about how rare complex life seems to be. And even that outcome, arriving after 42 years of crossing, after every cost this video has tried to describe, and finding nothing alive, would not be a failure. It would be one of the most significant discoveries in the history of science. Because finding no life at Alpha Centauri, at the nearest star system we could ever reach, would tell us something exact and devastating and precious about our own planet. It would begin to confirm that Earth is not simply one example among billions of similar worlds. It would suggest that what happened here, the 4 billion years of biology that produced oceans and forests and whatever it is that happens when neurons fire in a particular pattern and a mind briefly understands the universe, was genuinely rare. And if that is true, then the planet that crew member can no longer find in the window is not just home. It is almost certainly one of the most extraordinary places in this region of the galaxy. The search itself is what defines us, not the finding. The willingness to load everything we know onto a vessel we have never tested at that scale. Across a distance we cannot fully imagine. Toward a destination we are not certain will reward us, because we cannot imagine being the kind of species that looks at the nearest star and says, "Not worth attempting." We have never been that species. Not when we stood at the edge of Africa. Not when we pushed our boats into the open Pacific. Not when we pointed toward the moon with technology so primitive that the computers guiding the descent had less processing power than the device in your pocket. We went. We have always gone. And the grief at the window, the quiet undoing of looking for Earth among 10,000 identical lights and finding only the void looking back, that grief is not a reason to stay. It is the price of being what we are. It is, as best as we can tell, the most human feeling in the universe. So this was never really about Alpha Centauri. Not entirely. Not at its core. The distances are real, and the numbers are precise, and every obstacle this journey would demand. The decades of crossing. The radiation threading through the hull. The body quietly unmade by the absence of the world it was built for. The grief of watching Earth shrink into something indistinguishable from the 10,000 other lights in the window. All of that is real, and none of it was exaggerated to make the story larger than it is. But the reason to sit with those numbers, the reason to turn them slowly in your mind until the weight of them settles into something you can feel rather than just recite, has nothing to do with engineering and everything to do with what we are. Because here is what this journey actually measures. Not the distance between us and another star system. It measures the distance between a species that can want something and a species that can reach it. Between the animal that walked out of Africa with no map and no certainty and no guarantee of survival, following nothing more than a slow interior orientation toward the unknown and the civilization that looked up at that same sky 100,000 years later and began calculating trajectories. We are the only thing in this part of the galaxy, as far as we can tell, that looked at 25 trillion miles of empty and hostile space and asked, with genuine seriousness, what would it take? A 3-pound brain running on perhaps 20 watts of electrical activity looked at a distance so large that light itself takes 4 years and 3 months to cross it, and measured it, named it, began to argue about how to close it. That is not a small thing to have done. The universe is not made smaller by our ability to quantify it. It remains exactly as vast as it is. But the act of measurement, the fact that something as fragile and brief and biologically improbable as a human being can hold that scale in its mind, even imperfectly, even with the knowledge that the full weight of it will never quite land the way it should. That act is, in its quiet way, one of the stranger and more arresting things this galaxy has apparently produced. And it will end in a voyage, perhaps not soon, perhaps not within any of our lifetimes, or our children's lifetimes. But the argument for inevitability is simpler than it sounds. We have never, in the full span of our existence, been the kind of species that measures something and then decides not to go. The oceans got crossed, the poles got reached, the moon, with its guidance computers less capable than the device on your nightstand, got touched by human hands. The direction of travel has been consistent across every era we have any record of, and there is no particular reason to believe it stops at the edge of our solar system. So, if you are somewhere in the southern hemisphere tonight, and the sky is clear, and you look up and find Alpha Centauri burning quietly at the edge of the constellation Centaurus, the third brightest point in the entire night sky, steady and calm, and giving no outward sign of what it actually represents, you are looking at 4.24 light years of distance. You are looking at 25 trillion miles. You are looking at everything this video has spent its time describing. The radiation, the silence, the decades, the grief, the possibility of empty worlds, and the possibility of something else, the question of who would go and what it would cost them, and whether anything they found would justify that cost. All of that is compressed into a single point of light that looks, from where you are lying right now, deceptively peaceful. That is the thing about the stars. They carry no visible sign of what they demand from anything that tries to reach them. If you found something worth holding in this exploration of what it would truly mean to cross that distance, consider sharing it with someone who looks at the night sky and wonders the same things you do. There are more of those people than you might expect. Sleep well tonight, knowing that somewhere in the unfolding of human history, perhaps sooner than we imagine, perhaps across a time frame none of us will witness, that journey will begin. Someone will leave. And when they do, everything this species has ever been, every migration and every crossing and every moment of standing at an edge and going forward anyway, will be folded into the hull of the ship that carries them. Good night, and may your dreams reach for the stars.